Good morning. I am Tomo. Today, I want to introduce our student's paper by Terry and Yuan about our search for Planet 9. And then before starting, I want to thank all the collaborators. In addition to hardworking Terry and Yuan, probably sitting somewhere in the audience, all people in our group contributed a lot to this paper. Okay, so let's get started. Do you know how many planets are in a solar laughing? But do you know?
It depends on which year.
Which year? Okay, this year.
8.
Oh, yes, thank you very much. Yes, in our textbook we have 8, right? Wait, 1, 2, 3, 4, 5, 6, 9, 8. But no, there are 9. Actually, there are 9. I hope I can convince you by the end of this talk. Okay.
When I was in primary school, schooler, I know, we learned that it's 9.
Yeah, but Pluto, I explained. We don't count Pluto anymore.
At some stage, yes.
Okay, so I want to start with a very beautiful history. That is my favorite story. Every time I teach, I teach this. I enjoy teaching this class. So in 1781, Anders Lexell found that Uranus's motion is weird. Sometimes it goes faster, sometimes it goes slower. And then he suspected there may be another planet, which now we know it's a Neptune, maybe pulling or slowing down Uranus every now and then. But at that time, 1781, the observational data was not accurate enough to calculate this. But later, in 1846, British astronomer Adams and the French astronomer Leverrier independently calculated the position of the Neptune. At that time, observational data were accurate enough to be able to do this. And then Leverrier called the Galilei at the Berlin Observatory and then told him that, Neptune will be here. Please observe. Okay? And then Galilei at the Berlin Observatory observed the position that Leverrier predicted, and then within an hour he discovered, Neptune was there. So Galilei told Leverrier that it was really there, exactly where you calculated. And then sometimes people say Neptune was discovered by a pen and paper without looking at the sky. So this is, I think, there are a lot of theorists here in this room, right? So I think this is a very beautiful triumph of theorists. So that's a beautiful story, okay? Please keep this story in mind. And then now, let's get back to 21st century now. So before starting, I want to show you, so this is solar system. The outmost one is a Neptune. And then just outside of Neptune, there are a lot of thousands of small icy bodies. This is called Kuiper belt object. These are very small objects, but there are thousands of them just outside of Neptune. And then you can see many of these. Okay, this is okay. No, it's not okay. This is a long movie, so it's better to first. Okay. So this is Neptune's orbit. So it's just outside of Neptune. Okay, this is the topic of the day. Okay, then in 2004, Mike Brown and others discovered a very distant Kuiper belt object called Sedna here. Because telescopes are getting bigger and bigger, cameras are advanced, so we can now discover these kind of small bodies at the very distant universe. And then they observed this Sedna's object or orbit, and then it was like this. This is the orbit of Sedna. It's very different from other Kuiper belt objects, and this is already strange. Its orbit is elongated. To make object's orbit elongated, something need to perturb it. Okay, and then it's not Neptune because it's at least staying away from Neptune's orbit. if Sedna's orbit is overlapping with Neptune, something like this, then it's easy to explain. Okay, Neptune perturbed it when it's orbiting, the Neptune, kicked it out and then into elongated orbit. That's easy to understand. But it's not like this. Sedna is away from the Neptune's orbit. Then there remains the question, who perturbed Sedna? Right? This is a question one. And it was not just Sedna. In 2020, this BP113, this is Joe Biden, was discovered. Joe Biden, vice president. So nickname is Joe Biden. And it's also elongated orbit, and they're not touching Neptune's orbit. This is blue. And another one in 2015, Lelea Honua, also has a very elongated orbit, again not touching Neptune's orbit. Who perturbed this? And it didn't stop there. People discovered more and more distant Kuiper Belt objects, and then all of them, many of them, are elongated orbit, and then without touching the Neptune orbit. Who perturbed it? And then here, there's another strange clustering. So as you may have noticed already, these objects are clustering on one side of the solar system, and then almost all of them pointing the same direction. Right? All of them are here, and then there's nothing here, right? And all of them are pointing sort of this kind of direction. And I can show it in a movie. It's much more clearer in a movie. So these are orbits of these distant Kuiper Belt objects, and they are sort of almost on the same plane. You can almost put a paper here, right? It's on a plane, and they're all pointing in one direction, and then there's nothing on the other side. So in other words, they are spatially clustering in orbital space. And then why they are clustering in orbital space? This is very weird. This doesn't happen by chance. This is almost like you go to Taipei station, and everybody is looking at the same direction. This doesn't happen randomly, right? If you see something like this, there must be a reason. There must be something here, right? And it's the same thing. In this orbital clustering, there must be a reason. And in this case, there must be a dynamical reason. So something must have put their orbits into this kind of peculiar clustering state. Now, according to simulation by Mike Brown and others, this is 99.993% impossible. So we must have a dynamical solution to this. Okay, and the most reasonable dynamical solution for this is the presence of giant planet, we so-called planet 9, on the other side of the solar system. If there's a massive object on the other side, this object, by gravity, can kick out small bodies near its orbit. So that explains why these kind of objects are not on this side, and the only remaining small objects are on the other side of the planet 9, which are not, escaped from the perturbation. I can show that in a simulation by Brown et al. So here's the solar system, and here's the orbit of planet 9, right? And at the beginning, there are, you start with a lot of different orbits, everywhere. But if you notice, as time goes on, every now and then, on this side of the small bodies encountered with planet 9, and then they're kicked out of the solar system. So if you pay attention, sometimes these objects disappear, right? They're kicked out of the orbit. This is a long movie, and so I need to skip forward. But then soon, after a while, so there are more objects are kicked out from the planet 9 side, and then only small bodies remain on the other side of the planet 9. See, you don't see many. Sometimes objects disappear here, right? And then in the end, it looked like this. And this almost looked like the observed situation, no? This is simulation, but it looks very like observation, right? Okay. So, okay, let's keep it. So, with this kind of simulation, Brown et al. Predicted the presence of planet 9 with several times solar mass at something like several hundred AU with inclination of 16 degrees. So, and also, I want to emphasize this mass. Planet 9, according to this prediction, is a massive object. So this is a predicted planet 9. It's almost as big as Uranus or Neptune. It's much bigger than the Earth or Pluto. So Pluto is distant. It's smaller than our moon, right? So that's why Pluto was kicked out of the planet, right? Now it's a dwarf planet, but this planet 9 predicted one is a gigantic one, okay, to have enough gravitational perturbation to these small bodies. Then so after 80 years, we are in the same situation as 1846 when Leverrier calculated and predicted Neptune is here. We are in the same situation. Brown and others predicted planet 9 is there. So now we need to point the telescope. So the hunt is on. So a lot of astronomers in this field are hunting for planet 9. It's out there. We need to find it. And it's a big discovery. It's a giant planet. So a lot of people are hunting for that. But then a lot of optical telescopes try to find them. Pan-STARRS telescope, WISE telescope, Super telescope, Zwicky Transient Factory, Dark Energy Survey, OSSOS, this is kind of France Hawaii telescope. But none of them, until now, have found planet 9. Why? Why we cannot find it? It's because it's very distant. So several hundred AU, so it's almost 10 times, more than 10 times distant than Neptune. So it's going to be very, very faint in optical, something like 26 magnitude in visual magnitude. And remember, planets are reflecting sun's light. So the sun's light need to travel several hundred AU to the planet, reflected by the planet, and then need to come back to the Earth. So the brightness scaled with the distance to the -4. So that make it very, very faint. And then with this kind of faintness, even our largest telescope, it's very difficult to survey a large area to find it. Well, okay, Brown et al. Predicted the presence of planet 9, but the positional uncertainty is much larger than Leverrier's case. We have 100 degrees of uncertainty. So they just said, okay, around there. So we need to survey a large area to find it. So that's make it very, very challenging. So what should we do? So what should we do? So what we can do is, planet 9 is actually planets. All planets are low temperature black body. It's about 30K, 40K, something like that. And then they are actually very bright in infrared because the black body radiation peak of this kind of object. So this is Jupiter. Jupiter is very bright in far infrared because black body radiation peaks in around 100 micron or far infrared. Okay, so we can use far infrared space telescope to find it, right? It's bright in far infrared. Now, who has a far infrared space telescope? Oh, I shouldn't show that. I shouldn't show that. Who has the far infrared space telescope? Okay. I do. Here. This is our Akari far infrared space telescope. So when I was young, okay. 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 When I was young, I was working at Japanese Space Agency. This too loud? And I was in this Akari Space Infrared Telescope team. So the telescope is here. This thing is here. And then we launched. And then this telescope did the all sky survey in far infrared like this. So scan by scan, and then eventually it observed the whole sky. The telescope is not this small. It's actually 65 centimeter, so it's bigger than this. Okay, and then we did the all sky survey. So this is our far infrared all sky map. Okay, so this is our far infrared all sky map. So somewhere in this map, there is a planet 9 detected. All we need is hard-working students like Terry and Yuan to find the correct object among millions of objects in this map. Okay, so then Terry came up with the idea to combine another far infrared all sky survey satellite, IRAS, this is a European one, launched in 1983, with our Akari, which observed in 2006, and then try to find moving object from this survey to this survey because this planet moves on the sky. But then our telescope is only 65 centimeter. Is it sensitive enough to detect it? And it turned out it's actually, until like 600 AU or so, we can detect both satellites can detect planet 9. Okay, this is the detection limit, and it's okay up to 600 AU. And then how about the orbital motion in 23 years? So from here to here, 23 years, orbital motion is something like 70 arc-minutes. Okay, so we Terry need to find an object that moved about 70 arc-minutes on the sky. And this is what he did. So this is very important. We used specifically made single scan catalog that keeps the moving object. The publicly released catalog is not good for this purpose because public catalog was co-add of many scans. Then when you co-add many scans, they remove the moving object because it looks like garbage to them. So it's not good for us. So we specifically made a single scan catalog to keep the moving object. Okay, and then he removed the known sources by cross-matching other existing star catalog and galaxy catalogs, and then he found the pairs between. He did both of telescopes, and he made a search for pairs between here within 70 arc-minutes. That's the expected motion of planet 9 in 23 years. And then he came up with 13 remaining candidates, and then he eyeballed and then removed the noises, and then he came up with only one good candidate survived his inspection. Okay, and then this is this candidate. So it was detected in 1983 at this position, and then moved to this position in Akari after 23 years. So that's consistent with the expected motion of planet 9. And then we published this candidate in a paper which is accepted in April or so this year. And to our surprise, it caught a lot of media attention. So it was covered by Science Magazine and Universe Today. This is physics.org, and then this is ABC News, and then also Chinese newspapers, Taiwanese newspapers too. And then among them, actually 100 newspapers covered this. And I like the Science Magazine article the best because many of these only mention Terry's name, but the Science Magazine was kind enough to mention my name here. So I think they are very, very good magazine. And then it reached this attention score of 1,000, which is less than 0.1% of the paper gets. And then it was covered by a lot of YouTube video as well. And then particularly this guy, Anton's YouTube had surprising 400,000 views. So I'm very surprised. He must be making a good money out of this, you know. But we are not making. He's not giving any money to us, but he's making a lot of money. And one interesting thing is when Science magazine requested an interview with Terry, he declined. And so his paper appeared on archive on Friday, and they contacted Terry during the weekend. And then during the weekend, I was not checking email at that particular weekend. And then on Monday morning, I came to work and I saw Terry's email, which is quoted here, and I was shocked. This is a reply to magazine writer. He said, unfortunately, I usually have a class and group meetings on Monday, so I'm not available to have an interview with you. I am shocked to see this. I didn't know my group meeting is more important than Science magazine interview.
That means he's a very good scientist.
Yes, he's right there. Okay, okay, back to science. So we only have two detections, one from IRAS, one from Akari telescopes. And this is not good enough to determine the orbits. We at least minimum 7 detections to decide the precise orbit. So we need a follow-up observation. And then we are planning to use a dark energy camera on Blanco-Meter telescope in Chile for this purpose. So this is me when I was young in Chile at that telescope, and then now they have a new gigantic camera, so it's good enough to find its location. Okay, so let's summarize. We searched for Iris Akari moving object pairs, and then we found one good candidate, and then we're planning a follow-up observation to determine its orbit. So planet 9 is whispering now, and then it might be found or may be found in the near future. Okay, thank you very much. I stop here. Thank you, everyone, and thank you, organizers. Thank you very much.
Right,
thank you very much.
Interesting and nice story. So we can take some questions from the audience, please.
So Rubin telescope recently, or Rubin observatory recently started
Does it? Yeah.
data. Could they potentially see it?
Yes. Ruling is actually powerful. So yeah, if ruling start a survey, then it can see it. Yes.
Okay, so it's sensitive enough also in the wavelength.
Yes. Yeah. So we need to finish this before ruling ruling find it. So.
But they released already one picture. Have you checked?
Yes,
Already?
that's scary. They said they found thousands of asteroids already. So, that's very, very powerful.
But they released the picture already. Did you check the picture?
No, that's only tiny part of the sky.
It could be that it's yours part.
Yes, okay, yes, that's true. Yeah, well, we need to check if it's the same direction or not. Yes. Yes.
What's the smoking gun for the detector?
For smoking gun hole.
Confirm it, yeah.
To confirm, we need a follow-up observation and then.
How? What's the
So
what's the day? What's the future for your group to announce worldwide? We found planet 9.
Oh, so we have Akari detection, right? So we now have narrowed down the direction. It has moved since 2007, but then it's only a few degrees. So we just sweep these few degrees with this dark energy camera, and then if we detect a moving object, then that's confirmation. Now we know the position. We narrow down the position, so it's easy to follow up. Please.
Yeah, so can you go back to that picture showing the motion of the planet 9?
Yeah. You mean?
There is some reddish elongate features. Yeah.
This one?
Yeah, like you see there is some elongation factors, some red dots.
Here?
Then
Here?
actually up there, yeah. And is this the same kind of stuff from the red dots on the other image?
Yeah, it should be. It should be because we're looking at the same part of the sky.
It looks like the orientation is like different.
It is not the correct orientation. It should be. It should be this. Should be this.
Okay.
Yeah.
So you mean this way?
Yeah, it looks more like that.
Okay, Terry, can you check the orientation?
Yes,
Wait, what happened?
Yeah.
the orientation is correct, but because I think this 23 year separation.
Yeah, so
Hey,
that's
wait.
actually another question. How did you cross-match the position of the two catalogs? So I presume you know the precise orbit of this planet 9, so that you can do the cross-matching. You can you can calibrate the motion, right?
Yes, we
Yeah.
estimate the orbital motion within 537 AU, and then we search for possible pair within that angular separation range.
Yeah. So it was here before, here now. So here now. Here in 2006. So here now.
So is this, would this orbit be consistent with the simulations showing
That's a
curvature,
that's a
etc.? Is it how consistent is it?
That's an excellent question. Actually, it's not consistent. It's a little bit away from the predicted position of the planet 9 from dynamical simulation. So Mike Brown commented, "Okay, this is planet 8.5, not planet 9."
Is it good?
Yeah, I think the follow-up observation, can answer this. Yeah.
Martin? Could there also be then planet 10 and planet 11 or so? And how?
Yes, could be, could be.
So what is how would you, how do you define a planet in some sense, no? Because I mean, Pluto was not a planet anymore, and now you have another kind of planet. So how would you?
Oh, so the definition of the planet is it's a it's a it's a dominant object in its orbit. So here. So so here, to be a planet, it needs to be able to sweep out other objects from its orbit. In other sense, it needs to be as massive as these guys. Pluto is not massive enough to sweep out other objects in its orbit. So in other words, in Pluto's orbit, near Pluto's orbit, there are other small bodies. So so that's why Pluto is a dwarf planet. So to be planet, it needs to be a dominant one in its orbit.
I
Yes.
was thinking about do you have some reasonable estimate of the mass based on the flux that you measure in that
Ah,
planet? You know, because presumably this black body emission,
right.
you've got the flux and you've got some sort of temperature
Yes. So
range detail. So I guess it's a bit uncertain, but
yes, mass and
you know the
temperature.
flux and radius, and therefore may into a mass depending on the composition.
Right. Mass and temperature are degenerated. So we actually don't know the mass and temperature
Well,
in.
suppose you said it was 30 Kelvin, you know,
Yes,
original
yes, yes.
estimation.
To estimate.
Would
Yeah.
that give you a mass if it was mostly what, hydrogen? Is it the light, some combination of hydrogen and helium? Would
Well,
that give you?
well, to estimate mass, it's also another step because we only know the flux.
Yeah.
So
Well, like say you use I don't know, Uranus as a guide, right?
yeah.
Say the composition's the same.
Mm.
You could then, by analogy, get some kind of mass estimate.
Yes, yeah, we should be able to do that. Yes, yes. Ah, thank you, Terry. Could you estimate? Yeah, I think we should try. Yeah, thank you.
Okay. Can I ask a quick question?
Please.
So, do we understand that why this planet 9 is having such a huge orbit compared to the others?
Ah, that's
Like,
an
for example, if I
yeah.
see this, normally, in a factor of maybe 1.5 or 2 of the length of the year of the orbit, you will find another planet.
Right.
But this is like a factor of
Yeah, very different. Yeah, yeah, yeah. That's an excellent question. That's one of the scientific questions we want to answer. There are several scenarios. Like maybe Planet Nine is captured from other system in the or there are some other factors at the formation of the solar system. That's an open question. And to answer that question, we need to first find it. So that's one of the
Can we
scientific.
understand it from simulation data regarding the formation of solar system, for example?
Well, this simulation is assuming they put the planet 9 in some orbit and then see it's consistent with the capable object. So it's actually in situ.
Okay.
So and also this origin of the planet 9 depends on its orbit. So I think it's first to determine the orbit. It's important to see its origin to understand its origin. Yeah.
Okay. Okay. Thank you. Because of time, maybe we can take one really quick question, quick and urgent question with a short answer as well. If there's any, if there isn't any, let's move this.
Just one
Well, you have one.
Sure.
If that would be Planet 9, what would be the name? Oh.
What would be the name? Is it Terry Planet or something like that?
We can have a long discussion about this at coffee time. Yeah.
Okay.
All right. So let's thank our speakers again.
Thank you very much. Thank you, everyone. Thank you.